So I'm Simon McIntosh-Smith from the University of Bristol, and I'm going to talk about a project that my group has been involved with for a little time, which does involve a lot of the multi-core expertise we've got here in Bristol, both in the local industry as well as at the university. So what is this Mont-Blanc project? Some of you may have heard about this, but some of you may not. It's been running for a while. It's a European-funded project to explore if one of the major problems we've got in the future for really large computers is energy efficiency, then is it worth looking at, can we build systems from processors that have really focused on energy efficiency as their primary design goal, and see if building a supercomputer out of those gives us any fundamental benefits. So that's really what was behind this Mont-Blanc project, which has been led by the Barcelona Supercomputing Center, and the PI is a guy called Alex Ramirez there, with a number of other partners, some of whom are here. So I know there are some people from Bull here, and also Nodal. So lots of you know Nodal's a local networking company. They do fast Ethernet stuff. They've been one of the partners in this project. And it was really designed to look at, building a prototype system, finding out what the issues were, what are the software issues, what are the hardware issues, and does it give any benefit or not? We don't really know before we do this. So the reason why Bristol's become involved with this is, so one of the partners was already located here in the region, which is Nodal. And then my group actually got involved. We started using some of the prototype systems, and we had some very interesting results. As a result of that, we've been invited to be a full partner in the next system. So Mont-Blanc 2, the proposal for that's been in the commission for a while. We should know what's happened with that soon, and we can announce what's gone on there. But if it gets funded, Bristol will be one of the full partners in that project. And also this time, the team at ST here in Bristol has become involved as a full partner. So I think there are 12 project partners in Mont-Blanc 2 if it gets funded. And 3 of them are based right here in Bristol. So a quarter of the people in the project are based in this region. And if we include Alinea, so I see David at the back, that's another UK company. So 4 of the 12 are actually based in the UK. So this is evidence that we're good at this stuff right here in the UK. So where did this come from? Lots of people have said, in the past, we had big computers. They weren't quite so big in the 70s and 80s, but they were, fairly big machines, and they were very special purpose. Those of you who've been in high-performance computing for a while, these were special purpose machines. They were expensive. They were really fast at the time, and of course, Cray was one of the main vendors of these sorts of things. They were generally vector machines. They're programmed with Fortran and clever compilers and some other variants as well. But that was, by and large, how we did most high-performance computing in the 70s and 80s. And then something really major happened, which was the attack of the killer micros. And this was the PC industry grew really fast, became massive. We all bought PCs to have at home. And the funding that was going into that as a result, all the development dollars, pushed the development of the microprocessor very, very rapidly, so much so that it disrupted the traditional high-performance computing space. And the development of these vector processors couldn't keep up. So while initially the microprocessors that were becoming available from companies like Intel weren't as fast as an individual vector CPU, they were certainly a lot cheaper, and they were improving at a much more rapid rate. So maybe you needed 10 old x86 CPUs to match one old vector CPU, but they were a fraction of the cost. So very rapidly, lots of us in HPC looked at, can we build supercomputers from commodity parts, from CPUs, from mainstream vendors, rather than these big, expensive, complicated HPC systems from the traditional vendors. And actually, the disruption happened pretty quickly. So as an example, this is going back to our top 500, which is the fastest 500 computers that anyone's kind of measured in the world. And if you look back to not all that long ago, this is November 2000, so 12, 13 years ago, x86, as an example, was almost nowhere in that list of systems. So if you look at it, it was mostly IBM's Power, there was SunSpark, there was MIPS, which was SGI at the time, DEC Alpha, NEC, and then a tiny little sliver, 1.2% of the systems used commodity processors, used x86. that was just 12 years ago. We feel like we've been using Linux clusters forever, but it's not that long ago that all this happened. Fast forward 8 years, and bam, it's all gone. So the biggest slice, this is 64-bit x86 from Intel. This slice is 64-bit x86 from AMD. So within 8 years, nearly 86% of all of the systems were powered by commodity-derived processors, x86 processors. So completely disrupted. There are a few survivors, so IBM's power hangs on at the high end with things like Blue Gene, but almost everything else just got blown away by the disruption of the Killer Micro. So that was a big trend. So of course you then think, does that happen again? I should say there was a point when the fastest machine on the top 500 became an x86 machine for the first time. And it was the ASCII Red at Sandia that did that in 1997. It was the first 1 teraflop machine as well. It's the first x86 powered machine to get to #1. And it was with 32-bit x86. This is before it all went 64-bit. So this was still 32-bit addressing, but it got the #1 slot. Worth keeping that sort of thing in mind. So this has happened once. Could it happen again? So if you look at the commodity chain, we were really looking at how in recent times have desktop products disrupted servers and HPC. So there is an obvious next candidate, which is, well, the mobile space now is massive. We all know, for example, that this year the predictions from Gartner are 182 million tablets sold around the world, about 1 billion smartphones predicted to be sold this year. That's a heck of a lot of stuff. There's lots of development money going in there by lots of different vendors, including Intel, by the way. Obviously, I'm going to be talking about ARM a little bit in a minute, but everyone's going after this market with embedded processors. So we're really talking about embedded processors designed very much with a consumer focus in mind and how they might disrupt higher levels of the market. And some of the vendors, so for example, even if we take a quick look at ARM, they have been starting to prepare for things like this. This is a chart just showing how they've been adding support for 64-bit floating point, right? Does an embedded, small, energy-efficient, low-cost processor need 64-bit floating point? Well, it's getting it, and it's got it pretty fast. So we're already up at about 4 double precision floating point ops per cycle in the latest version of the ARM architecture, and it's still rising. So they're kind of getting ready for this kind of space. They're taking it seriously. And even the GPUs that companies like ARM and Imagination have been developing, they've become very programmable, very flexible. Then you can program these with some standard languages like OpenCL. The current Mali 604, which is in lots of things shipping today, it's about 68 gigaflops of compute, single precision. There's another one that's going to be out soon that's a few hundred gigaflops. There are GPUs from other vendors with similar sorts of performance at very, very low power. So this is a couple of watts. The kind of performance we're talking about here is just a couple of watts to do this. And you can tell from the talks we've had through the day, these kind of areas are really important to the ARMs and the Imaginations of this world. They're focusing on this very much. So we're expecting this to kind of carry on. So can we exploit that kind of thing? If you look at it right now, the ratio between a core optimized for the embedded space and a core optimized for the high end, the ratio in performance is quite distorted. So about 1 in 8, something like that. So this might mean a really fast top-end core from Intel would give you, let's pick some arbitrary numbers, 8 gigaflops, and maybe the equivalent Atom from Intel will get you about 1 gigaflop. So it's quite a big ratio. Or this could be an ARM core to a high-end x86 or something. But the ratio in cost can be a lot bigger, because obviously it's hard. You have to put a lot of effort in to get these really, really big numbers, and you're into diminishing returns in terms of the hardware you use. So the costs can be at a different scale to the scale in performance, the ratio in performance. As the embedded processors get jacked up and they start going faster and faster, this is not just ARM, but Atom as well, they catch up. So they're catching up in terms of performance. What will the ratio be in cost? Well, I can't believe they can catch up magically. There has to be some cost to that. So I don't believe the ratio is going to stay the same. But it might still be an interesting sweet spot. It might be an interesting sweet spot to explore. you might get more performance per dollar, and maybe more performance per unit of energy as well. So it's worth looking at this, and that's really the crux of this Mont-Blanc project, is exploring whether there is something about the mobile space and designing for that we can exploit for high-performance computing. The added benefit being we're actually really good at this stuff in Europe. So if it's true, there's a good potential economic benefit to all of us who are working in this space in Europe. As at the moment, the vendors who dominate the high end are generally outside of Europe. We've got the ARMs and the imaginations of the world, etc. Companies like ST that can manufacture that stuff right here. So there may be some extra benefits if this is true. So there have been a few prototypes built. I believe somebody earlier on mentioned the Tibidabo prototype. That's the one my group first started to use, which was fairly Keith Robinson thing lashed together. It's already been moved on to a new version of this. Both of those involved NVIDIA GPUs and ARM processors. There's a new prototype in the works at the moment, which I think Anton mentioned earlier on from ARM, which is an all-ARM system. So it's a Samsung chip with an ARM CPU and an ARM GPU all in the same chip. And that's what the new one's going to look like, which will be coming out fairly soon. And the project isn't just about the hardware. It's also been getting the Linux stack working, or the compilers, the maths libraries, and sometimes there were things missing, so the project's been kind of filling in some of the holes to make this possible, so you can run fairly standard high-performance computing software stacks on this kind of hardware. So this is the processor that's in the new prototype that Anton mentioned earlier on, from Samsung to multi-core, ARM A15, nearly 7 gigaflops just on the CPU. It's not bad, but nearly 70 gigaflops on the GPU, which is really good. And again, this is just for a few watts, and it is a cache coherent shared memory structure across the whole thing, which might give us some options for doing something a little bit different with the programming models in the future. So that's what we're going to be playing with real soon. And Bull, who's a partner in this, is building a special enclosure. So each one of these little cards have some of those chips on, and you can pack these in really close together. They're fairly low power, so the cooling isn't too tough to do. And then you can build a big system by racking up lots and lots of those things. So is this going to work out? We don't know. So it looks quite promising. But of course, there is no magic, and I agree with what Jim was saying earlier. There's no magic in terms of one ISA versus another or anything like that. It's really a question of picking design points and seeing what works for you. For me, actually, the most interesting thing about this question of does ARM really bring anything to high-performance computing, it's the different business model it brings that's the most disruptive. It's the fact that actually it could be an NVIDIA part, or it could be a Samsung part, or it could be an ST part, or it could be anyone who fancies having a go at doing something different or radical for a multi-core thing optimized for storage or HPC or who knows what. That's what could be most interesting and different about this. It's not really one RISC ISA versus a CISC ISA. It's not, I think that's kind of missing the point about what's really happening here. But it's definitely worth looking. It's definitely worth looking to see if this is going to give us some real economic benefits in Europe, because we are good at this stuff, as we've seen. My gut feel is at the moment, the hype about getting all this stuff going and mobile processors might be more energy efficient, we're probably past the peak of the hype. We're probably somewhere heading towards the trough of disillusionment, and the results will look like, well, hey, it's not as fast, so it's not quite so interesting. But maybe eventually we'll come out the other side. Maybe it'll be a whole bunch of atoms or something like that. But it's definitely worth looking at. There's some interesting questions to answer. So anyway, there you go. That's a very quick run through this Mont-Blanc project. It's exploring this stuff because we're good at it in Europe. Bristol's playing a growing part of that, and the UK more broadly. It's targeting open standards. You've heard OpenCL mentioned quite a lot, because we can actually write nicely heterogeneous, adaptive, parallel programs in OpenCL. And one of the things my team's bringing to the project is we have a whole bunch of software that already uses that, and we can get this running really fast on embedded processors, on Xeon Phi, on NVIDIA GPUs, on AMD GPUs, on anything we try. It runs really fast on CPUs as well with vectors. So some of these things are out there, and you can go and play with these emerging languages if you're serious about trying this. That's it. So I will stop there. Thank you very much. That was the last one. And we've got 1 or 2 minutes for questions. Let's see, 2 hands have gone up.
So can you tell us a little bit more about the Mont-Blanc project in terms of how big is the system going to be, how many cores?
Yeah, so right now it's really only building prototypes because it's trying to work out if, even on a small system, does it actually have any real benefits? What are the software issues and things like that? The plan would be, if it does look like it's going to be a real benefit, to even Mont-Blanc 2 is going to be prototype based. After Mont-Blanc 2, then it starts getting serious, and it's going to start building systems that would be hundreds of teraflops on the way towards the next scale machine. So right now, these projects are of the order of millions of euros. When we start building real systems at scale, we're going to be asking for 100 million euros or something like that. So we're still a few years off before we get we need the big checkbooks to come out.
And bearing in mind what other speakers have said about the importance of designing the interconnect, how does that figure in your approach?
Well, that's really where Nodal comes into this. So the interconnect between nodes, that's what Nodal brings to the project. Within nodes, that's varying at the moment as we go with different vendors for each of the processors. So I guess it's using ARM's Amber for what's in the latest generation of the chip. Yeah. Okay. And there was one more over on this side. Oh. Yeah, got time, James.
Nowadays, I'm less interested in capability computing. I'm quite interested in capacity. A long time ago, I had an IBM salesman do the whole blue jean pitch, and he said, I've got 25 kilowatts I can cool per rack. Folklore, urban legend, whatever you want to call it. Government's going to have about 5 strategic G-Cloud data centers. And that's, for me, that's more about capacity. So the number of things and services and stuff I can host, and not about capability. Is anybody here, or are you particularly looking at that kind of thing, how much you can fit into a rack, 42 U's for some row of fridges?
Yeah. I guess there's 2 parts to that. One is the density, and then the other is the energy efficiency. And you might have space limitations, but you might also have, we know we can have this much power and that's it. So I want to get all of my compute for a certain amount of power. All of that stuff is one of the things that's driving Mont-Blanc. But actually, even if you look back at the major vendors now, so for example, I know Intel's looking at microservers built from multi-core Atom stuff, where it's really focusing more on sort of throughput or capacity rather than capability. So lots of lighter weight cores rather than fewer heavier weight cores. So I think the market is slightly sort of diverging a little bit. There's now people are recognizing there's different kinds of workloads for which there are lots of customers. And I think even the Facebook and all that side of the market actually doesn't necessarily need the heaviest weight cores. They might actually just want lots more slightly lighter weight cores, especially if that's more cost effective. So there are, as well as Intel, there's vendors like Calxeda who are now doing multi-core ARM stuff for servers. There's AMCC are doing multi-core for servers as well. So there's a whole range of new things starting up, which should be interesting to see what actually comes out of that. I'm always expecting there to be something to come out of Asia as well. So someone somewhere has got to do something radically different. Huawei or somebody is going to say, hey, all of a sudden we've got this dirt cheap thing. That should be able to happen now, but I haven't seen it. See what comes out. All right, good. We will leave it there. So it's just time for the afternoon break. So I'm guessing there's tea and coffee outside? Tea and coffee outside. Yeah, it's half an hour. Then after that, it's the tool demonstrations. They're in half-hour slots. There's more than 3, so you won't have time to see all of them. but do pick the ones that you'd like to do and go and see those. And we're back in here at 5 for what should hopefully be a very controversial panel session. Get your questions ready. Yeah, that's it. Thank you very much. See you later.